In the previous video, we started taking a look at the binomial experiment, giving it a definition, and then being able to work with the binomial experiment to define whether or not a scenario was binomial. So now we're going to take it a step further, and let's just say we do have a binomial situation or scenario, experiment, whatever. And now what we can do is we can go through and we can start doing some number crunching with this. So we can always find the mean of a binomial distribution, and it's actually pretty easy. We're going to define that as n times p. The standard deviation, which is probably one of the nicest standard deviation formulas we have in this course, is n times p times q. And of course, there's always a not so nice formula. This one is the probability of success of exactly x outcomes in a binomial distribution. So we might remember our old friend from a couple videos ago, the combination. So we have this n combination x, and we have p to the x, q to the n minus x. And of course, we need to define what p, q, and n are, as well as x. So p is the probability of success. And again, that has to be given and it has to be fixed. If it's not given, nor is it fixed, it's not a binomial experiment. The complement of p, or 1 minus p, is q, and q is the probability of failure. X is going to be the desired number of outcomes, and then the sample size is going to be n, which again has to be given and fixed. And so those are our formulas, and given those formulas, let's go ahead and see if we can work a problem that involves the binomial distribution. So a very classical sort of problem is being able to predict gene types, allele types, being able to predict eye color, etc., and even blood type. And in fact, a lot of times, blood donation sites, they really target people that have certain levels of blood because they know it's rare, but how rare is it really? So we have a national study, and it shows that approximately 6% of all people have type O negative blood. Let's say for some reason we study 16 randomly selected people, and they have their blood type recorded. Right? And the first thing we want to do is we want to determine if it's binomial, which means that we have to go through those 4 different possible outcomes. Right? So remember, the first thing that we have to do is we have to identify if the number of outcomes is fixed, and in this case it is, it's 16. Independent. Okay, so is my blood type contingent upon some stranger's blood type all the way out in Wisconsin? Right? And certainly not. Okay, so blood type for randomly selected people, and again, we always go with randomly selected, is independent. The third scenario is, are there 2 outcomes, success or failure? So what is a success? Well, success in this case is O negative blood. And what's a failure? Well, failure is going to be no O negative blood. So you either have O negative or you don't have O negative. All right, so now we know that there are a number of other blood types, A positive, O positive, A positive, A negative, etc. All right, but we don't care about those. We just care about either getting O negative or not getting O negative. And then the last case is the probability of success known, and is it fixed? And the probability of success is, in this case, 6%. So ultimately what we can say is, yes, this is binomial, which might not be good for you because that means that we have to do the other parts of the problems. All right. So now we can go ahead and do the rest of the problem. So to be able to find and interpret the expected number of the 16 people that have O negative blood, the first thing we probably want to do is we want to figure out what n is and p is. So let's just gather some variables. We know that n in this case is 16 people. We know the probability of success p is 6% or 0.06. We know that q, we go right up here, which is the probability of failure, is 1 minus p. So 1 minus 0.06. And we can go right to our calculator because our calculator doesn't lie. 1 minus 0.06 is going to be 0.94. And now we can start to go ahead and find some of the formulas. So mu, which is n times p, is going to be 16 times 0.06. Okay, so n times p, and that should be 0.96. But again, we don't trust me. because of course we only trust the calculator. So 16 times 0.06, not 1 times 0.06, even I can do that one in my head, is 0.96. Now, that's the expected value, but what does that mean, right? Is that 96%? No, it is not. All right, very common response I get from students is that they think that that's a percentage. It is not, okay? What this means is that we expect that of the 16 people, or randomly selected people, 0.96, okay, or really about 1, would have O negative blood. I'll just say O neg blood. All right, so again, the expected value is the number we expect to have. It's not a percentage. Right. Letter C asks us to be able to compute the standard deviation and then determine what number of people would be outliers. So we have our formula. So we're going to go back up here. We see our formula is the square root of n times p times q. So sigma equals square root n p q. And we know n is 16. We know p is 0.06, and we know q is 0.94. And how do we know that? Well, we're literate. We just see it right here. Okay, we figured it out before. We just substitute that in. Let's plug it into the calculator. So we're going to say second square root 16 times 0.06 times 0.94. All right, and that's going to give us 0.9499. Right, or 0.95 if you want to round it. It doesn't really matter. I'll just go to 0.9499. All right, now, one of the other things that we remember is that we have to also figure out what number is going to represent an outlier. All right, and you might remember from before we defined an outlier is that if x is greater than mu plus 3 sigma, or if x is less than mu minus 3 sigma. All right, and we just found mu to be 0.96 plus 3 times 0.9499. And then this would be 0.96 minus 3 times 0.9499. Okay, so remember, this was the definition that we gave of an outlier earlier in the course. So we still have to remember that those exist. All right, so we're just going to go in our calculator. We have 0.96 plus 3 times 0.9499. And that's going to be the upper bound, 3.0897. So we could just say 3.81. And then we can do that trick where we just hit second, enter. And we could just change that plus into a minus. And that's probably going to be a negative number. So it's not even going to make any sense. All right, so we have 1.89889. So we can say 1.89 negative. So we have 3.89. So we have x is greater than 3.89, and then x is less than negative 1.89. All right, and that doesn't make any sense, but this one certainly does. Okay, so basically what we're saying is an outlier, and this one doesn't make any sense. All right, I think we used the phrase nonsensical before. We'll just say nonsense. But if we get more than, or we could just say 4 or more. So if we get 4 or more O negative out of 16, this is an outlier. All right. In other words, it's a very rare occurrence. All right. So we might want to trust or choose not to trust those responses. All right. So finally, we're going to start computing some of the probabilities. Right? So for letter D, we have to go all the way back, find the probability that none of the 16 have O negative blood. So this is our formula. So we're going to hold on to that formula. Let's just copy it down here. So we have P of x is equal to n combination x, p to the x, q to the n minus x. We want none of them to have O negative blood. So in this case, X is going to be equal to 0. So probability that none of the 16 have O negative blood. All right, so we're just going to substitute that in. So we're going to say P of 0 is equal to N, which is 16 combination 0. We know that P was 0.06 raised to the 0. And then Q, which is 0.94 raised to the 16 minus 0. All right, now, here's what I would suggest so that way you can input this correctly. First, figure out the combination, okay? Or you could just type it in all at once. I'd suggest you figure out at least this, right? So I'm just going to type it all in, all at one time. So we're going to say in parentheses, 16, and you might remember you have to go to math, and you have to go over to probability NCR. Okay. And then you're going to multiply that by 0.06. You're going to raise that to the 0, right? And don't forget, you might have to hit the right key to get out of there. And you're going to multiply that by 0.94. We can raise that to the 16th power, right? And then we're going to hit enter. And that gives us 37,157, so 37372 approximately. Right? So we go back here, and that's going to be approximately 0.372 or 37.2%. So it's very feasible that we could line up 16 people, and there's about a 37% probability that none of those 16 people are going to have O negative blood. All right, last part of the problem. Find the probability that 1 or 2 of the 16 have O negative blood. So we're going to do the exact same problem, except we're going to do it twice. All right, so for letter E, we're going to find P of 1. Then we're going to find P of 2. And we're just going to add those together because it's an OR problem. All right, so P of 1, we have 16 combination 1. P of 2, we have 16 combination 2. And again, we're still using this formula. All right, this is a formula you absolutely want to have. 0.06 times to the first power, and then we're going to multiply that by 0.94 to the 16 minus 1 power. And then down here, it's the exact same thing, except we're going to replace all the 1s with 2s. All right, so let's go ahead and figure these out, and then we can add them together. Right, so we're going to go in our calculator, and here's a trick. We can just hit 16 or second enter, and we're just going to change everything. All right, so remember it was 16 minus 1 for the first. All right, so right here, 16 minus 1 is 15. And then we're going to go back and change this 0 to a 1. Oh, one last time. I forgot to change this 0 to a 1 at the very beginning. Okay, so that's a 1. We're going to hit enter. All right, so we get 379. Right, so this is going to be 0.379 plus. So we're going to do the exact same thing. We're going to plug in 2. So second enter. So now instead of 15, 16 minus 2. Oh, let's go back. So we're going to change all these to 2s. Right, so this is going to be 16 combination 2. And then 0.06 to the second. And instead of 15, we're going to make that 14. And we hit enter. All right, so 182. All right, if we add those together, that should give us 5, 1, and then 7, 8. So 561. But I'll just go ahead and check it in the calculator just to make sure. So we have 0.379 plus 0.182, and that's 0.561 or 56.1%. All right, so hopefully that's an overview of how we're going to utilize the binomial distribution. All right, so hopefully the next problems will go a little bit easier now that we've seen it. All right, but what I might suggest is Go ahead and try example number 2 on your own, right? So that way you can see if you know what you know, if you know what you're doing with this, or if you need a little bit more remediation. All right, and then go ahead and watch the next video, which will demonstrate the solution to this.